Hello everyone, today we're going to talk about heat transfer, and this is going to be our basically first class that we are trying this, meaning I will pre-record everything and hopefully you will look at the video in full length before the class, and then during the class basically I will answer any question you have and I might go through some basics in here. So let's dive in and talk about heat transfer here. Heat transfer is going to be basically, we will explain about the last equation that we have, which is the fifth equation. Remember, we had 5 unknowns, which were the 3 velocities and temperature and pressure. We could find out and we could solve for 3 velocities and pressure in using Navier-Stokes equation and continuity equation. Now the fifth one, which is somehow independent in a sense that you don't need it for solving the other 4, but we're gonna discuss it, so it's gonna be a full circle now. Okay. It just stopped working. Just a minute, I'll fix this one. Okay. So let's go into it. So why we are studying heat transfer? Obviously heat transfer is very important for many different subjects, and it could have any reason, actually many reasons to be interested in heat transfer. It could be that you want to find out the overall heat transfer over your system. Usually, of course, this is a solid, but in fluid mechanics it could be a fluid inside the system, a chemical reaction, a heat transfer from one liquid to another, for example in heat exchangers, and so on and so forth. So or you could find the highest and lowest temperature in the system. That is actually something crucial in many systems. For example, if you remember in our first session, we talked about cooling of the motherboards and the heat transfer on them. So in that aspect, you want to know how is the heat distribution on your motherboard and what's the highest temperature on it. Of course, temperature distribution, another thing. Again, in for example, heat exchangers. Then you have temperature response in time dependent heating and cooling. For example, you want to see what is the fatigue coming from cooling and heating on your system, and many more reasons: cooling, heating, so on and so forth, in HVAC and so on and so forth. So that there could be many reasons why you are interested in solving for heat transfer. This is the general energy equation that we have, and again, I don't want you to memorize this equation. What I want you to know is the different terms inside this equation. So you have the unsteady term, which basically solves for temperature as a function of time. You have convection, conduction, which are 2 different types of heat transfer, and we will discuss them shortly. Then you have species diffusion, which is basically distribution or transfer of heat due to diffusion of one liquid into another. Example, you have a pot of water, you put a hot ink inside that water. So ink starts to diffusing inside water, and by diffusing it, it will also change the temperature profile inside your water. Then you have viscous dissipation, which is basically friction, and that comes between different layers of liquid. As you know, for example, inside the pipe, the flow on the wall is 0 velocity, and it increases as you go further from the wall. So these different layers of fluid with different velocities, they create friction between each other, and and the friction causes heat transfer and heat dissipation, which is called viscous dissipation. Then of course you have enthalpy source, which is basically generation of heat inside your system, or it could be negative consumption of heat inside your system due to, for example, some reaction. So you have unsteady term, convection term, conduction term, species diffusion, viscous dissipation, and also enthalpy source and of course sink. So let's dive into the methods, dive into the definitions. Basically, the first and most obvious one is conduction. In conduction, what happens by definition is a diffusion of heat due to temperature gradient in material. So this happens in a molecular level, and basically means your objects, if you have two objects, has to be in contact. If you have one object, this is the heat that is being transferred or distributed through vibration of the molecules. Then the second one, you have convection. In convection, heat is carried away by moving fluid. So in this one, you actually need a body of fluid to move around, to transfer the heat for you. The flow can be be due to external forces, for example, a pump, a compressor, a fan, so on and so forth. So the driving force behind the moving fluid could be external. That's called forced convection, and or it could be natural convection, meaning there is no external force, but due to some different reasoning, the fluid is moving. That's called natural convection. That's called natural convection or buoyancy force. Then of course you have radiation, and you didn't have the radiation in the original energy equation. That comes through the heat source and sink in your equation. But radiation is transfer of energy by electromagnetic waves between two surfaces. So this is the only method of heat transfer that actually does not require any material to be to transfer the heat. So remember, in conduction you need molecules, in conduction you need a moving fluid, but in here you don't need none of that, and because it's through electromagnetic wave. And this is actually the method, you know, that we receive this heat from the sun, right? So radiation is very important in high temperature. As you go to lower temperatures, meaning below glowing temperatures where your material is literally glowing, if you go below glowing temperatures, what will happen is basically radiation is not as important as the others, and it can be neglected. So let's move on to our first method of heat transfer, heat conduction. Heat conduction is very simple, and it is based on something called Fourier's law. So in Fourier's law, what we say is that the amount of heat transferred through a material, please look at the cursor, mouse cursor to follow, amount of material moved. Let me change this actually to laser pointer. Okay, the amount of material moved in here from high temperature to cold temperature, that Q is, and of course we divide everything by cross section to make it even, but that heat transfer is proportionate, remember, proportionate to delta T. And of course here shouldn't have a K, so sorry for this is a typo, so this K shouldn't be here. So Q is proportional to temperature gradient, meaning the difference of temperature between cool and hot area. So that's proportionality. And in mathematics, you know from mathematics, a proportionality can be turned into an equation if you add a constant. Okay, so if you add a constant to an equation, to a proportionality, it becomes an equation. Now that constant for us is Q. Remember guys, again here is a typo, there shouldn't be K. So that constant for us is K. So when we add this K, it becomes an equation. And please just neglect negative comes only because of convention, so to make it right for higher and lower temperatures. So when you add K, it becomes an equation, right? But remember, K, which is called thermal conductivity, is a man-made parameter and has to be measured in laboratory for every material. The way they measure it is basically they plot Q based on temperature gradient, because temperature gradient and Q can be independently measured in laboratory. Okay, so they put any material they want to measure the K for it, and for different temperature gradients they measure the amount of heat transfer, which this creates a line. The slope of that line is your K. So that's how they determine K for different materials. Okay, now let's move. So the next one is convection heat transfer. In convection heat transfer, as we mentioned earlier, the heat is being transferred through movement of fluid. So you need a moving fluid to transfer heat. For example, you see the example here. You have a box, and the box is in higher temperature than the fluid passing over it, and the fluid is in cold temperature, but as it passes over the box, it gets heated and the heat is being transferred down the stream, as you see. But this heat is not through conduction, and it is through convection, and this convection is actually forced convection, because the cold water that is coming from the left hand side is probably being driven by a compressor or actually by a pump, right? So that's called forced convection. In here, remember, this is one example of heat transfer. This is the forced convection, but it could be natural convection, which we will get into that in a minute or so. So remember, guys, in the orders of different heat transfer methods, the highest amount of heat transfer is convection, if you are comparing convection to conduction. Okay, so the highest order is convection, and between the convections, the highest order is forced convection. So forced convection is first, then then you have natural convection and conduction. Always remember that. So anywhere that you have forced convection, you can basically neglect natural convection and conduction. You have experienced this a lot. You have seen this in winter. You see in winter, when you have your jacket on and you're walking outside and it's cold temperature, -20, -25, as long as there is no wind, you don't feel cold. But if it starts blowing for even less than a minute, you will start getting very cold, although you still have your jacket. The reason for that is, as soon as wind starts blowing, the transfer mode changes from conduction from the surface of your jacket to convection through the surface of your jacket. And as we said, convection and forced convection is a couple of order of magnitude larger than conduction. That's why in winter you feel cold in that condition. So let's look at the convection equation. Convection equation comes from something called Newton's law of cooling. So basically the heat transfer, which is Q, is proportional to the surface area of the object, and a temperature difference. The temperature difference between the free stream temperature, the T infinite, and the body temperature. And again, don't forget, this is a proportionality. So the Q in convection is proportionate to the surface area of that object and the temperature gradient between the body and the free stream flow. To make this into an equation, we add something called H, which is called average heat transfer coefficient. So by adding H, basically you make that proportionality into an equation. But But guys, remember, H is much more complex than K. So it's not as easy as calculating K. So H is flow dependent, meaning you cannot calculate H for wood or for steel. It depends what the shape is, what the temperatures are, what kind of conduction heat transfer is, so on and so forth. So for H, basically what you need to do is you need to find that out for every single problem. So remember, K is the property of material, and H is the property of the flow. Let me turn back this into oops. Okay, now let's look at different methods of convection heat transfer, since this is the general formula for it, and as I said, H should be calculated for different flows, not different materials. It depends on the flow. So let's look at some examples. So the convection heat transfer coefficient can take different shapes, different equations, and different ranges depending on what problem we're talking about. Here are the three most common examples. Of course, in this class we will go through only the first and the second, which are the natural convection and forced convection, and boiling convection is not for our class. So anyway, the natural convection, which we said is one of the subcategories as opposed to forced convection, your H is usually proportionate to the gradient of temperature to the power of x, and x could be something between 1/4 and 1/3. And what actually determines x depends on the material, on the condition, and the temperature ranges, and should be discussed case by case. In forced convection, H is actually constant because we are artificially creating that flow, so it is on but depending on our system, we can define one H and usually one average H. And remember, for this purpose of this class, or generally for future problems, usually you will be provided by natural convection or forced convection coefficients. The last one is boiling convection, and in boiling convection, H is proportionate to the delta T to the power of 2, and the number could range anywhere from 300 to 900,000. Boiling convection is a type of convection that is happens during the boiling, and this is one of the examples. For example, you have a pot of water, you put on the stove, it starts heating up, and it starts getting to the boiling point, and small bubbles form on the bottom of the container, and eventually they start rising up to the top and creating the boiling condition. This is called boiling convection. So now let's move on to the next major, actually to the first major subcategory of convection heat transfer, which is the natural convection. So in natural convection, there is no external force. But as we know, in convection, by definition, you require some sort of movement inside the flow. And if we don't have any external forces, where does this movement comes from? So the answer is, when you create temperature gradient inside a flow, inside the fluid, sorry. And for example, somewhere is at 80 degrees Celsius, the other places are in 20 degrees Celsius. And we all know that the the density of the fluid is dependent on temperature, meaning as you increase the temperature, the density goes down. As you decrease the temperature, as you increase the temperature, density goes down. As you decrease the temperature, density goes up. So when you have inside your flow some places at 80 degrees and some other places at 20 degrees, obviously their densities would be different. The fluid in 80 degrees will have a lower density or will be less heavy than the other places that are at 20 degrees. And because we have gravity, remember, natural convection works if you have some sort of gravity in your system. If because of gravity, anything with lower density has to move up, and anything with higher density has to move down. And this is the reason we are having natural convection. So in natural convection, a flow is induced inside the fluid because of difference in densities, and because lower density has to go up and higher density has to come down. This is what happens actually when you have you remember those old heating elements that you had in the rooms. When you had those, the heating units, which basically were usually aluminum, there was hot water inside, and it would heat the air and creates higher temperature everywhere inside the room. The way they were working is they would actually heat only the radiators, you had in the room. The radiators only would heat the air in their immediate vicinity. But when the air got heated in their vicinity, that air density drops and that the air moves up. And since you can't have vacuum inside the room, cold air would take the place of that hot air, and again the cycle repeats itself. The cold air gets heated, goes up, so on and so forth, and this creates a circulation inside your room that basically distributes heat everywhere inside the room. So this is called natural convection. So in natural convection, basically your force, the force that is moving the flow, is proportional to the difference of density at higher temperature and the density at standard temperature, of course, multiplied by gravity, because it depends on gravity. Depending on where you are, on Mars, on the moon, or on Earth, you're gonna have different natural convection forces. The important dimensionless number for natural convection is called Rayleigh number, which is basically somehow is the ratio of conduction to natural convection. So Rayleigh number is a non-dimensional number that will give you an indication of if you have to consider natural convection or the natural convection is negligible in your system. And remember, if you have forced convection in the system, you don't need to calculate Rayleigh number, because we know if we have a forced convection, nonetheless what happens to the natural convection, the order of magnitude for forced convection is much higher, so we only consider forced convection. You will go about calculating Rayleigh number if you only have conduction and natural convection. Now, if the Rayleigh number is below a critical value for your fluid, heat transfer is primarily in the form of conduction, and when it exceeds that critical value, heat transfer is primarily in the form of convection. Now, calculating Rayleigh number is easy, but what is difficult is actually come up knowing what the critical number is, because we said you have to have a critical Rayleigh number which below that heat transfer is the form of conduction, and above that heat transfer is in the form of convection. Now the answer is unfortunately there is no one generally accepted number for that critical Rayleigh number. It depends on many things that what the critical Rayleigh number is. It depends on the different fluids that you have, the temperature ranges, the type of convection, type of phenomena that happens in the flow, and so on and so forth. So it is something that has to be discussed case by case. So now we have to also talk about something called Boussinesq model. So this Boussinesq model is related to natural convection. And we are explaining this because, generally speaking, calculating for natural convection, especially in simulation, is a bit difficult. The reason for that is, if you want to really calculate natural convection as is, you have no other way than considering your density to be temperature dependent, which means your density is not constant anymore, which means you are going into compressible flow. Although the changes in density is not extreme in natural convection, and it is in no way a conventional compressible flow, but still it's not constant. Density is not constant. It is function of temperature. If you assume density as a function of temperature, it will make your simulation more difficult, because remember, you're adding another unknown to your 5 unknowns. The density becomes unknown too. Now, in order to make the problem easier, especially for industrial and practical purposes, we have something called Boussinesq model. In Boussinesq model, basically what it says, okay, consider density to be constant, then compensate for the effect of natural convection as a source term in your Navier-Stokes equation. So basically add a source term to your Navier-Stokes equation, which compensates for the force of natural convection. That force, that source term that you are adding, is calculated like this. It is calculated by multiplying rho naught, which is your fluid standard density at room temperature, by something called beta, which is expansion coefficient, multiplied by temperature of the flow minus the standard temperature, and of course multiplied by gravity. Okay, so this is the equation that we will be using in Ansys. So in Ansys or any other actually software, you have two options. One, assuming density is a function of temperature and solving that, but that would be a bit difficult, though not impossible, but difficult. The other way is using Boussinesq model. When you use Boussinesq model, remember, and always remember, for Boussinesq model you need three values. One, your rho naught, g, and beta. Remember, if you don't assign a value for beta, or if you don't assign g or activate gravity, you will not see natural convection in your system. Okay. Now, the next one is the next subcategory, which is forced convection. So in forced convection, as we said, what happens is you are having an external force creating the flow for you. So in here, you don't need temperature gradients to have density gradients to have the flow. Although, remember, in forced convection, you might also have natural convection as well as conduction. But remember, for the sake of being practical, we only take forced convection. We only calculate forced convection itself and neglect the natural convection and, of course, conduction here. So in forced convection, what happens is you basically have an external force moving the flow inside the system. In here, for example, is a pipe, and the temperature, the heat is basically being carried away by that flow movement. In forced convection, one thing you have to remember, especially in places that you have long surfaces like flat plate or pipes, is that when you have forced convection, you're going to create a heat transfer boundary layer, same as flow boundary layer. Remember, you had flow boundary layer and fully developed flow in terms of momentum. Exact definitions also comes into effect for forced convection and temperature. So next one is conjugate heat transfer. In conjugate heat transfer, it is not a category in our heat transfer methods. It is just a combination of some, and we are mentioning it here because it involves solid. This is probably, not probably, is actually the only subject that we are also using solid in our system. So in conjugate heat transfer, basically it is convection through the fluid combined with conduction through the solid. And of course, you know, the only method of heat transfer inside a solid is conduction. And I'm emphasizing inside because if you're talking about surface of the solid, it is most probably, it could be convection, it could be radiation. So if you're talking inside the solid, it is only conduction. And as I said, conjugated heat transfer is a combination of convection in fluid plus conduction inside the solid. So for example, here you have two solid circles with high temperatures and you have a flow passing over it. In this case, you see we have the heat transfer inside that plus convection in the fluid. Now, here you could have solved this in two ways. One way would be like this, which means you are considering the solid inside your simulation domain, as you see. So in here, you have to solve the heat transfer inside the solid, but the upside is you're going to have the heat distribution, temperature distribution inside the solid as well. The other method was just to carve out two solids, so that your domain would be like this, and you wouldn't mesh the solids. In this way, the solids would act only as boundary, and this is gonna be only fluid system. And basically, what happens is you're gonna solve only heat transfer inside your fluid and not inside the solid. We will try to solve an example for the conjugate heat transfer, and if not, we will upload an example for it. So the last but not the least is radiation heat transfer. In radiation heat transfer, basically thermal radiation is defined as emission of energy as electromagnetic waves. As we said, you don't need material substance to transfer this, so it can be transferred in vacuum as well. So in radiation heat transfer, as we mentioned, because the heat transfer is through emission of electromagnetic waves, the intensity of the heat transfer through this method depends on the body temperature and surface characteristics. So these are the two important things: the body temperature and the surface characteristics. And this becomes basically important mode of heat transfer at very high temperatures, and we mean very high temperature. It has to be either a combustion or a solid that is literally glowing from high temperatures. But other than that, this can be neglected, and actually we tend to neglect this because, as we will see in a moment, calculation of radiation heat transfer is extremely difficult, both in terms of the equations and the statistical system that involves that is included in it. So remember, if it is not absolutely important, it can be neglected, and usually it is important in special cases in nuclear reactions, if you're talking about stars, if you're talking about the glowing subjects, so on and so forth. Okay, so moving to the next slide. So there are many different radiation heat transfer models, but all of them are basically based on surface characteristics. Now, the surface characteristic is defined by three different characteristics. One is called absorptance, the second one is reflectance, and the last one is transmittance. So basically what they are is absorptance is a coefficient that determines how much of the heat which comes to the surface of the object through radiation can be absorbed by the surface itself, and of course increasing the temperature of the surface. The reflectance is a coefficient that is basically measuring how much of that radiation is being reflected from the surface going some other places. And of course transmittance is a coefficient determining how much of the radiation is passing through the object. So, and they have defined them in a way that their summation is 1, and that kind of makes sense because the summation of all these three, the energy that is in all these three phenomena should be same. The summation should be same as the incoming wave of energy. So any model that you see out there, now I wouldn't say 100% of them, but definitely 99% of them are based on these three characteristics. So they differ in a way of they are calculating these characteristics, how they relate these characteristics, and how they actually relate different surfaces to each other. There are different models in Ansys Fluent for radiation. You have the RTE, which is radiative heat transfer equation. You have discrete ordinate model. You have DTRM, which is discrete transfer radiation model, P1 model, Rosland model, many different models. We're not going to get into the nitty-gritty of these models because they include extreme calculation, very difficult and complex mathematical equations, and so on and so forth. But you need just to remember all these models work based on these characteristics, and that's it. But remember, the only difficulty with radiation heat transfer is not actually the equations. The difficulty is one big part of the difficulty is actually in the volume of calculation that is required for this, even for a very simple problem. Consider this: you have around 10 objects inside the room, and you could admit that 10 object is a very underestimation of number of objects in a typical environment. But even if you have 10 objects and each of those objects are transmitting, radiating, so now you have to deal with many arrays of heat that is being transmitted from each object. Then every single of those arrays hit some surface, and some of it being absorbed, some of it being reflected, and some of it being transmitted. And so basically every array divides into 3 different arrays that you have to follow. Soon you will end up following of billions and billions of arrays. So regardless of the model you use, the amount of calculation that you need for such problems are really enormous. That's why we say wherever you can neglect it, because that would change calculating radiation, would change everything in your simulation. Now, we talked about different heat transfer models, about convection, conduction, and radiation, but let's take a step back and look at the bigger picture that we have, that basically why we are calculating these. Of course, we discussed this in our first slide that yes, we are calculating these for the purpose of calculating maximum, minimum temperatures, heat transfer coefficients, heat transfer rate, temperature distribution, so on and so forth. But the bigger question is, why do we need those? So we need those basically to optimize our system for heat transfer. Now, remember, optimization could mean anything depending on our system. In one system, decreasing temperature could mean optimization, while in another, increasing temperature could mean optimization, right? So generally speaking, in different heat transfer modes, in conduction, convection, radiation, we need to optimize. And we optimize that by tweaking the parameters. Now, how do we keep tweaking them is, for example, by increasing the area. If you increase the area, of course, you are increasing heat transfer. Or by increasing delta T, you are increasing the amount of heat transfer, and so on and so forth, increasing H, decreasing K. The point is, usually in the problems that you have to solve for heat transfer, what happens is, you usually need to change different parameters to optimize system, and the parameters you would change depends on your heat transfer mode, conduction, convection, radiation, so on and so forth, and based on those, depending on what equation you're using, you can change cross-section area, temperature gradient, and so on and so forth. Now, moving on from this, we have to discuss some Ansys specific parameters. So these Ansys specific conditions are basically different boundary conditions. Let's have a look. What are the boundary conditions in Ansys that we have to consider for heat transfer? You could have constant heat flux, you could have constant temperature, and in convection you can have free stream, temperature, wall thickness, convection coefficient, so on and so forth. So in CFD simulation, thermal boundary conditions usually are either at the walls or at the inlet and exits of the flow. If you're talking about inlet, usually you have to supply fluid temperature. At the exit, you should supply the backflow temperature. You remember we talked about the backflow, which was if you have some sort of circulation close to the exit of your flow, some of the flow from the exit will enter the system instead of exiting it. So you need to provide backflow pressure as well as temperature for it. So, but usually, as I said previously, for backflow you don't need to have a very specific number. As long as it is within the range, it would be fine. So it has to be within the range of the system, and that's basically a guesstimate that you are making. If you're talking about wall, because remember, other than the exit and inlet, the chances are the most boundary conditions for heat transfer that you will provide is for the walls. So on the walls, you have to have either specified heat flux, so you have to provide what is the heat flux on the wall, what's the constant heat flux on the wall, or you have to provide specified temperature. For example, you say no, the wall is constant temperature, and let the system calculate the amount of heat transfer. Or if you are talking about convective heat transfer, you of course have to provide H on the wall. Or even if you have radiation, it's you have to have the surface characteristics, material characteristics to calculate the external radiation on the system. So a review of the dimensionless numbers that might come to use when we are talking about heat transfer. One is Nosov number. Nosov number is the ratio between convection and conduction. So wherever you have both these phenomena, you usually calculate Nosov number to see if the convection is dominant or conduction. And remember, if you have forced convection, usually the Nosov number is very high because, as I said, convection is much higher than the other methods. Then you have Grashof numbers. number, which is ratio of buoyancy forces to viscous forces. So the buoyancy forces are natural convection forces, and viscous forces are the forces of the flow due to viscosity, viscous dissipation. Then you have Prandtl number, which is the ratio. This is useful for diffusive system. For example, when something is diffusing another material, that's when you have the Prandtl number, and this is basically between the momentum diffusivity and thermal diffusivity. So how much, for example, going back to the example of ink inside the water, so the momentum diffusivity is how fast the ink itself is diffusing into the system, and thermal diffusivity is how much fast the heat from the ink is diffusing inside the system. So the Prandtl number basically gives you the ratio of these two. And of course, last but not the least is the Reynolds number, which is the ratio of inertia forces to viscous forces. You might say, okay, this is a Reynolds number. What has it to do with the heat transfer? Because it is basically the ratio of momentum forces to viscous forces. The reason Reynolds number is very important, and generally speaking, the reason that Reynolds number is arguably the most important non-dimensional number in fluid mechanics is that, for example, in heat transfer, Reynolds number determines if your flow is laminar or turbulent. And we will see on our turbulent example, once we get to that point, that being laminar or turbulent has a great effect on the amount and method of heat transfer in your system. And just as a side note, generally speaking, as a general rule of thumb, any turbulent flow comparing to any laminar flow in, of course, similar scenarios, similar systems, turbulent flow has couple of order of magnitude more heat transfer considering to laminar flow. So remember, just as a side note, and this is just a side note, and we will discuss it once we go to turbulence in more details, but whenever they want to increase the amount of heat transfer, they try to make the flow turbulent. Okay, now before ending this chapter of our course, we need to basically discuss one more thing, and that's other temperature dependent parameters in our system. So when we include energy equation in the equations that we are solving, okay, it means we have a temperature parameter. For that reason, there could be other parameters of usually the fluid that can be temperature dependent. So let's look at, let's have a quick look at them. Of course, before moving to those other parameters, the most important parameter first and foremost is density. So density could be temperature dependent. One example we talked about was natural convection, but that's not the only one. There are many different ones like ideal gas, incompressible ideal gas, real gas, so on and so forth. You see many models here. So if your density is changing based on any of those equations, remember, when you are setting up your materials in your material dashboard, you have to change the density from constant to any desired model. And even if you see here, you have the Boussinesq. So when you are solving for a natural flow in the Ansys, there are three things that you have to do. First, activate the gravity. Second, change the density model to Boussinesq. Third, and arguably the most important, give a value for beta, the expansion coefficient. If you fail performing any of those three tasks, you will not see your natural convection. And the bad news is your system will not give you any error. It will not give you any hint. It will solve the system because there is nothing wrong with the system. But the only difference is you will not see natural convection. You might ask, if I'm choosing Boussinesq here and a beta coefficient shows up here, doesn't it have a value? The answer is no. The value by default is 0. So remember, always remember to put a value for beta, activate gravity, and of course the change density model to Boussinesq. So let's have a quick look at different models that we have in for our density. One is the ideal gas law. You know what the ideal gas law is. Your density here is not constant anymore. It's being calculated based on pressure divided by R, which is the universal gas constant, the temperature, and also molecular weight of your substance. So here the flow is not, the density is not constant, whereas it depends on the pressure and temperature of your system, and of course the property of your material, which is its molecular weight. If you have incompressible ideal gas law, basically the density is being calculated from the same equation. The only difference is this is not anymore dependent on pressure. You see here it is dependent on pressure. It makes it compressible, but here it's only depends on the operating pressure, which is a constant number. It doesn't depend on the local pressures. Now, density for natural convection, this is what I explained already. You put on Boussinesq and give the value for beta, and of course don't forget about gravity. So the other thing is density as a function of temperature. So your density could be simply as be a function of temperature. One very obvious example of it is natural convection. You remember, because we said in natural convection the natural way of simulating it is assuming density is a function of temperature. Now you could go with Boussinesq model. That would be one way of it, of course the easiest way of it. But even if for any reason you wanted or you had to consider density as a function of temperature, you could use this model. But you have to, of course, decide about the type of the function, piecewise linear function, piecewise polynomial function, or a polynomial function. You have to decide about that, of course. And also you have to provide the coefficients in here. So what the coefficients are, what the equation is highly dependent on what you are solving, and basically the general rule of thumb is use the best case possible. Use the best equation, best coefficients that basically represent your case. So moving on from density, the next parameter is specific heat. So basically the specific heat, or CP, could be constant, as you can see here, and it could be a function of temperature, and again it could be different function of temperature. It could be piecewise linear. Here you can see it could be piecewise linear, it could be piecewise polynomial, or it could be a polynomial function. So again, same as density, what you choose, what function you choose, what constant you choose, highly depends on your system, on your case, and you have to decide case by case. And usually you will use these functions. Usually that's the reason, not all the time, but usually you use those functions basically because you have an experimental background. basically meaning you have been through some sort of experiment, or you have performed some sort of experiment, or you are trying to simulate and regenerate the result of some experiment, and from those experiments you know a specific equation for your CP, for your density, for your K, so on and so forth, and for that reason you have the equation and you have the coefficients. So the point is, usually you use equations for density, for CP, for K, if for some specific reason you have the coefficients for it. Otherwise, using these functions would be a bit difficult, at points impossible, because essentially you don't know the coefficients, you don't know which one represents better. And remember, in CFD, if you don't have enough information, it is better to stick to the previous, to the more simpler models with predetermined coefficients, which are abundance of them in Ansys. So the next parameter that could depend on temperature is thermal conductivity. You remember we said thermal conductivity, or K, is usually a constant that is being calculated for every material, and still that is true. If you go to the Fluent database, you would basically see for every material you would see one constant K. But here the point is, in some materials, in some more complex systems, you might need to actually calculate K, because it's not constant anymore, and it can change basically by different values. Not only even temperature, it can change by many other different parameters. So for that reason, Ansys has given you the capability here to calculate K whenever, of course, again, you don't want it to be constant. Whenever you don't want this to be constant, you use one of these models. The models, the functions, are similar to the others that we have already discussed. It could be, again, piecewise linear. It could be piecewise polynomial. It could be even more models here. You see the kinetic theory, user-defined function also. One thing you might see in all of these choices, in all of these drop-downs, are user-defined functions. This one. And use user-defined. Basically, that's the capability, and we will discuss this in our last session when we talk about user-defined functions. You will use this capability basically whenever you want. They have put actually this capability in the system for you to provide your own system, your own functions. So basically, the logic behind this is, okay, you're not happy with the models already populated with Ansys. You can't fit your data in any of those piecewise linear, piecewise polynomials. Okay, fine. Go and write your own program and attach it, your own code, and attach it to Ansys. So that's, again, user-defined is a more general subject, and we will discuss it once the session comes. It is included in our session, which we talk about transient flow and user-defined functions. Okay, moving on to our last slide. Last but not the least, of course, actually one of the more important ones is viscosity. We have discussed this in short lengths in our previous sessions. So basically, viscosity, same as any other material property, can be constant, can be changing with different parameters. So viscosity, but the subject of viscosity is a bit more complex than the subjects of Cp, K, or H, because when viscosity is constant, we are talking about a Newtonian fluid. As soon as you change it to non-constant, it doesn't matter what kind of non-constant function you use, as soon as you change it to non-constant, it becomes non-Newtonian fluid. And generally speaking, solving non-Newtonian fluids are a order of magnitude more difficult than Newtonian fluids. But if for any specific case you had to use viscosity as non-constant, as a non-Newtonian, there are many models in here that would be applied. You can choose between them that will be applied to your system. And again, if none of these models suits your system, you can again go with the user-defined functions. Okay, guys, thank you very much for listening. And again, I hope you listen to this video before the class. And of course, during the class, we will further could discuss this or answer your questions. I have done this basically because there were a bit of complaints from different people, because our class timing could be uncomfortable for some of your colleagues that are in different time zones. So I started saving, pre-recording the sessions. Then during the sessions, and of course it wouldn't be a 3-hour session, much shorter sessions on Fridays and 1-hour sessions on Wednesdays. Basically what we'll do is I will try to quickly go over it if possible, and if not, answer your questions. Thank you very much and see you in class.